In this video, we solve problem 6.1.10 from Nagel's Fundamentals of Differential Equations, 7th edition. The problem statement says determine whether the given functions are linearly dependent or linearly independent on the specified interval and justify your decision. Now, I will say that this problem came from the spring 2021 Differential Equations quiz number 4. Because of the pandemic, all of the students had to take their quizzes at home. It was after spring break, and so we didn't want to go back to campus if we could avoid it. So I'm going to show you sort of what I would have expected you to do to answer this question on a paper-based quiz, and then I'll show you how to get the answer that MyLab Math is seeking from you. So it says, determine whether these functions are linearly independent or linearly dependent on the specified interval, and then justify your decision. The easiest way to do that is with the Wronskian. So we're going to compute the Wronskian of these three functions. And the way that works is you're going to evaluate a 3x3 determinant. In the top row, you're going to have your three functions. In the next row, you'll have their first derivatives, and then the next row, you're going to have their second derivatives. So remember, the derivative of tangent is secant squared of your angle. In this case, the angle is x. And then the derivative of secant squared requires the chain rule. Remember, the derivative of secant squared can be thought of this way. We write secant squared x, but what we really mean is take secant of x and then square it. So this function is on the inside. The derivative of this composite function can be found by taking the derivative of the outside first. The derivative of a function squared is 2 times that function. You put the function back in, and then you multiply by the derivative of the inside by the chain rule. So it's the derivative with respect to x of secant of x. Now remember, that's what this notation means. This is an operator. It operates on this. This whole thing is the derivative with respect to x of whatever's in the brackets. In this case, that's secant of x. And the derivative of secant of x is secant of x times tangent of x. So I've got 2 times secant times tangent, which we would write as 2 times secant squared x times tangent of x. Now that goes here. Okay. Now in our second column, we have a cosecant function. And the question becomes, well, what's the derivative of cosecant? The derivative of cosecant is negative cosecant of your variable times cotangent of your variable. Remember, all your trig functions actually need to have angles inside. You need to be able to take the cosecant of something, so there should always be a variable there. Now, when I take the derivative of this product for the next line, I need to use the product rule. So I'll think of this as my first function, and that over there is my second function. So according to the product rule, we'll get the derivative of the first times the second. Undifferentiated, you just leave it alone, plus the derivative of the second times the first. And again, the derivative of cosecant is negative cosecant cotangent, and a negative times that negative will be a positive. So we'll have a positive cosecant of x times cotangent of x here. And then the derivative of cotangent of x is negative cosecant squared x. So we have a negative 1 times cosecant squared x. Now, I've got to simplify a bit. I've got a cosecant and a cotangent, so that's cosecant of x times cotangent squared x, and a negative cosecant squared times a negative cosecant of x. That's going to give me 3 of those multiplying each other, and a negative times a negative is a positive. So we'll have cosecant cubed x. Now, if you want to, you could factor out a cosecant of x from both of these. So you have cosecant of x times cotangent squared x plus cosecant squared x. And you might think that you could simplify that in some way. Perhaps cosecant squared x and cotangent squared x satisfy this relationship. 1 plus cotangent squared equals cosecant squared. That's one of our Pythagorean identities. So we could write this entirely in terms of cotangent by replacing this cosecant squared with 1 plus cotangent squared. Or we could write this entirely in terms of cosecant by replacing this guy with cosecant squared x minus 1. Either way is fine, actually. Or you could just leave it like this. I think I'll leave it like this. I'll leave it in this form because I don't think that factoring really helped us much. Although it may help later when we're expanding this 3 by 3 determinant. Okay, and then in the last column, we'll have the secant of x and its derivative, which is secant of x times tangent of x. And then its derivative by the product rule. I'm not going to write out the work for this one. Well, actually, maybe I should write out the work for this one. Always a good idea. When in doubt, show your work. Use the product rule again. There's my first function. There's my second function. And I've got the derivative of the first times the second, undifferentiated, plus the derivative of the second times the first. And the derivative of secant of x is secant of x times tangent of x. And the derivative of tangent of x is secant squared x. Hopefully you notice that it's very similar to what we did up there. And you have secant times tangent, so that's a secant of x times tangent squared x. And I've got 3 secants over there. Okay. Don't forget your angle. Secant x, tangent squared x, plus secant cubed x. Wow, that's a lot. So now I want to evaluate this 3 by 3 determinant. I can expand along any row or column that I want. I think I will expand along this one, just the first row. Remember your sign convention, it's going to be plus, minus, plus. When you write this in terms of smaller determinants, 2 by 2 determinants in this case. So the Wronskian of these 3 functions is positive 1 times tangent of x times the 2 by 2 determinant that comes from crossing out the row and column containing tangent of x. So I want that 2 by 2 determinant. This is my first column and that is my second column. You can write it down if you want to. You don't have to. If you don't want to, you can skip this step. You can actually just evaluate the 2 by 2 determinant instead. That is totally fine with me. But since I'm making a solution video, I am going to show my work. So I want everybody to be able to follow along. Just in case it's not obvious for some folks, and that is totally okay. Okay, so we're going to evaluate that in a little bit. Minus cosecant of x times the 2 by 2 that comes, or the determinant, 2 by 2 determinant that comes from crossing out this row and this column. So we're going to have minus cosecant of x times this 2 by 2 determinant. Got that 2 by 2 in the first column there, or that, I guess it's a column vector with 2 items in it, 2 rows. And then I've got the next column vector, which comes from the third column over here. We're crossing out this guy and this guy, and we're looking at these 2 guys. Same thing as we had right there. Last one, we're going to have a positive secant of x times this 2 by 2. Now, one of the downsides of this is that we're working with trig functions. So if we evaluate all of this and it turns out that everything cancels out and we get 0, we're going to say that these are linearly independent for all x values, or these functions are linearly independent on any interval where, of course, all the functions are well defined and so on. Um, but sometimes it's not going to be obvious that it's zero because maybe it actually is zero and it's written in terms of trig functions and you can't tell. So we're going to have to be careful about the way we write this so that it is sort of obvious that Wronskian is either zero or non-zero. And actually, there's not really a rule or a method for doing that. It's really just up to us. Okay, so we're here. Now let's expand. We have tangent of x times this times all of this. So what I would recommend is that you multiply these two guys together and distribute. We're going to do this in one step. So I have this, I'm thinking of it almost as a monomial. We're not dealing with polynomials, but it has one term. We're not adding or subtracting things from each other. We just have this one expression here. And I've got a sum of two expressions over here. So I'm going to distribute over addition. This guy gets multiplied by this guy, and this guy gets multiplied by that guy. So we're going to have tangent times negative cosecant of x, cotangent of x, times secant of x, times tangent squared x. Oops. And then we have this times that, minus cosecant of x, cotangent of x, times secant cubed x. All of that minus this times this. And you're subtracting when you multiply across this diagonal. So I'm going to think of multiplying negative secant of x times tangent of x times both of these quantities here. And I still have that multiplied by the tangent of x on the outside, and I ran out of space, so I'll keep doing that. So I have negative 1 times this times this. So I've got secant of x, tangent of x, cosecant of x, cotangent squared x from that first term, and then this times this. It's going to be a minus because, again, we're subtracting negative secant of x, tangent of x, cosecant squared x. All right, that's the first part. Now, before we keep going, before we go on from here, I'd like to simplify where I can. Do you remember, I hope you remember from trig, that tangent and cotangent are reciprocals of each other? Like tangent of A is equal to 1 over cotangent of A and vice versa. So tangent is sine over cosine, cotangent is cosine over sine. There's reciprocals. With that in mind, whenever you multiply them together, you should get 1. If I multiply both sides by cotangent of A, I get 1. So every time I see a cotangent times a tangent, I can just eliminate that because that times these two guys multiplying each other, if the angles are the same, it's going to give me a 1. So I got cotangent of x and tangent squared x. So one of those is going to reduce. And I think that's it. All I can simplify there. I can remember that tangent is actually sine over cosine, and cosine of x is 1 over secant of x, or a. I'm using a for angle. So cosine of a is times secant of a is equal to 1. And I will keep that in mind as well. Sort of an aside, we actually don't need that yet. But let's see, what else can we reduce? Is there anything else we can reduce? Tangent times one of the cotangents will be gone. And I guess we'll leave the rest of this alone for right now. Okay. And then on the next one, we've got negative cosecant of x times this times this. So I'm going to have secant squared times secant times tangent squared. So there's going to be 3 secants there and a tangent squared. I've got 2 of these and 3 of those. I'm going to have 5 of those. I'm going to multiply across that diagonal, and then I'll multiply across that diagonal. We're subtracting, so we have minus 2. We've got a secant times 2 more secants, that's going to be 3 secants. Tangent times tangent is tangent squared. That's right. Okay. So that's for this part. So we've got 2 terms from here and then 1 term from there. 1, 2, 3. Okay, we're good. And actually, we got 2 terms that are like terms. I've got one of these here and another one of those here. One of them, then I'm subtracting 2 of them. So I'm going to end up with -1 of those. So I guess we can say this, and then we can change that to just a -1. Okay. Keep going. And then the last one we've got plus secant of x times this times this. We've got secant squared x times cosecant of x times cotangent squared x. And then I've got secant squared times cosecant squared. Let's cross that diagonal. Bam. And then we're going to multiply across that diagonal and subtract. So subtracting a negative is going to mean we're adding it. I've got 2 of these and nothing repeats. So I've got secant squared tangent of x and then cosecant of x cotangent of x. Wow, that's a lot. Okay. So we're trying to simplify as much as we can. A few things that we want to keep in mind. Tangent of an angle is sine of the angle over cosine of the angle. And we also know that sine of A and cosecant of A are reciprocals. So sine of A times cosecant of A is 1. Cosine of A and secant of A are 1. Or times secant of A is 1. Because cosine and secant are reciprocals of each other. And tangent times cotangent is 1 because those 2 guys are reciprocals of each other. Okay, so with that in mind, I'd like to simplify wherever I can. First, I'll write this tangent as sine of A over cosine of A. And let's see what happens. Well, sine of A times, or sine of A, these are the angle in this case is x. We've got a sine of x here and a cosecant of x there. When they multiply, that's just going to give me a 1. And then I've got a cosine in the denominator here and a secant here. So that's actually 1 over cosine times secant. That's 1 over cosine is the same as secant. So it's a secant times a secant. So what we actually have there is this red tangent from the outside. It's still there. We haven't done anything with it. And this is just sort of scratch work, so you want to ignore it. And then we've got secant times a -1. So that's going to be negative secant squared x. All righty. Over here, we want to simplify wherever we can. Remember what cotangent is. Didn't put that down here. Cotangent of A is cosine over sine. So this is cosine of x over sine of x. And cosine times secant, the angles are the same as 1. So this will reduce with 1 of these. So we'll have 2 of those left. And I have a 1 over sine, which is the same as a cosecant times a cosecant there. So I've got negative cosecant squared x times secant squared x. Okay, so far so good. All right, down here, we've got a secant, a cosecant, and a cotangent after that 1 cancellation. And remember, cotangent again is cosine of your angle over sine of your angle. This cosine times the secant is going to be a 1. And so I'll have a negative cosecant times 1 over sine, which is another cosecant. So that's going to be a negative cosecant squared. From here, and then over here, see where we can reduce anything if we can. Tangent is sine over cosine. And the reason I'm writing this in terms of sine and cosine and then thinking about these is so that I can get 1s. I want things to simplify. So I've got a sine times a cosecant. That's going to give me a 1. Okay. And I can't do anything else with what's left. So I've got a secant times a 1 over cosine. 1 over cosine is secant, so it's a secant times a secant. It's going to be a negative secant squared times the extra cosecant that's still there. All right. That's the first 2 lines. Keep going. We said this was a negative cosecant of x times, like we have a secant to the 5th minus secant cubed x tangent squared x. Okay, let's see if there's anything else that reduces. Cotangent is cosine over sine. So this is cosine squared x over sine squared x. And cosine and secant are reciprocals of each other. So cosine times secant is 1. So cosine squared x times secant squared x is 1. Okay, and now I've got a 1 over sine squared, which is cosecant squared, times another cosecant is going to be a cosecant cubed. This piece simplifies to cosecant cubed. I don't see anything that reduces there because there are no tangents or cotangents to rewrite. And then on this guy, I will write tangent as sine over cosine. And cosecant is a reciprocal of sine, so these guys multiply. Well, actually, yeah, we could do that, but it's easier to simplify something else first. Rather than doing that, sorry, let's get rid of the tangent and the cotangent. So we've got 2 secant squared x and a cosecant of x. And I've run out of space. So I'll just write that there, but don't forget it's multiplied by that extra secant on the outside. Okay, trying to simplify if possible. So what I would recommend we do next is maybe factor out a negative secant squared x from this. So we have a negative secant squared x times that tangent of x. And the secant squared x times a positive 1 would give us this guy. And negative secant squared x times the cosecant squared would give us that guy. Okay. And then over here, I guess we could factor out a negative cosecant squared x. And then we're left with a 1 plus secant squared in those brackets. There's a similarity here, but it's just different enough that sort of nothing reduces. I wonder. Okay, just keep going. Then over here, we've got a negative cosecant of x, and these have a secant cubed in common, so I'll factor that out. And then I'm left with a secant squared x from here minus tangent squared x. Now here's another fact. 1 plus tangent squared of some angle is equal to secant squared of that angle. So if I subtract this guy from both sides, I get 1 equals secant squared of my angle minus tangent squared of my angle. So this guy is actually 1. That's nice, that works out. Let's see if we have something similar happen over here. We've got a secant of x in the red, and then I see that these guys have a cosecant squared x in common. And then I'm left with an extra cosecant here and a secant squared there. And then we still have this last term. I guess I'll just distribute. I've got a secant and a secant squared, so that'll be 2 times secant cubed x times cotangent of x. All right, so I got one little cancellation there. Nothing else canceled. So I guess I'll just distribute and see if there's anything that cancels after distribution. So I have negative secant squared tangent of x times 1. So we're distributing back through the parentheses. We factored everything out because we were hoping that there would be some cancellations, and there weren't. And then we've got this times tangent. Oops, tangent of x. Over here, you've got minus cosecant squared x tangent of x, minus cosecant squared x tangent of x times secant squared x after distribution. Okay, over here, we just have a negative cosecant of x times secant cubed x times 1. And then here we have a secant of x times cosecant cubed x. And this quantity times this quantity is going to give me a positive secant cubed x cosecant squared x. And then the last one is positive 2 secant cubed x cotangent of x. All right. And actually, I don't think that that's supposed to be a cosecant or cotangent. I believe it's supposed to be a cosecant because that came from this term over here. We had the tangent and the cotangent that reduced, and we had 2 secant squared times cosecant times an extra secant. So this should not be a cotangent. That should be a cosecant. That is a big error to make because it would change the value of your answer quite a bit. Let's see if there's anything that reduces. Do you have any copies of anything? See anything twice? Oh, I've got 2 of these. I've got one of these here and one of those there. So we can group those together. Negative 2 secant squared x cosecant squared x times tangent of x. So the blue expressions are gone. And then here, I guess we've got cosecants and tangents. We don't have those anywhere else, so I can just write those down. Negative secant squared x tangent of x minus cosecant squared x tangent of x. Okay, done and done. Down here, I've got 2 of these here, and I'm subtracting one of them, so now I have one of them. Secant cubed x times cosecant of x. Bam. And then here, they look similar, but they're not the same actually. I've got a secant times cosecant cubed plus secant cubed times cosecant squared. Of course, with angles. Okay. What do I notice? What do I notice? Well, with these guys, I notice that we've got secants and cosecants multiplying each other. And if I were to try to factor out something from these guys, they all have at least one secant. They all have at least one cosecant. So we could factor out a secant times cosecant from those. Up here, they all have a tangent factor in common, and we've got a secant squared and a secant squared and a cosecant squared and a cosecant squared. But I don't know that that's going to help us really with much of anything. So let's say we factored a negative tangent of x there. Then we would have, let's say, a positive secant squared x plus 2 of these plus 1 of those cosecant squareds. And you could factor out a cosecant squared from this, and you'd be left with 2 secant squared plus 1 times the cosecant squared, or you could factor out a secant squared from this, and then you'd have 1 plus 2 cosecant squared times the secant squared x. But I don't see how that will help us at all. It's not going to help anything reduce. Oh well. And then down here, if we factor out a secant of x times cosecant of x, we've got secant squared left there, and we've got a cosecant squared left there. And here, we took out one secant and one cosecant, so we'd have secant squared x times a single cosecant. Again, I'm not seeing anything that reduces really nicely. So that was a lot of work, and I think that we can say that that's not zero, knowing what we know about our trig identities. So we'll say that the Wronskian of these three functions, which started as tangent, cosecant, and secant, that Wronskian is non-zero, so the functions are linearly independent. Okay, now another thing that you can think about, especially when you're talking about the linear independence, is not using the Wronskian. Instead of doing all of that, you might just think about what it means to be linearly dependent or linearly independent. So we say that the set of functions f sub 1, f sub 2, and f sub 3 is a linearly dependent set on an interval I if there exist constants C1, C2, and C3 such that C1 times F1 plus C2 times F2 plus C3 times F3 equals 0. And these are not all 0. Now, if the only way to get this to be 0 is for the C1, C2, and C3 to be 0, then we say that the functions form a linearly independent set on that interval. So let's think about this relationship for our functions, tangent of x, cosecant of x, and secant of x. So you might say to yourself, is there any combination of these three functions that you could add together to get 0? And I don't think there is. And we're on the interval from 0 to pi over 2. That was given to us at the very beginning of the problem statement. I think the only way that you're getting 0 out of this is if all three of those are 0. Remember what your tangent function looks like. On the interval from 0 to pi over 2, we're just talking about this part of the curve. And of course, this repeats infinitely many times, but we're just going to look at this first part, and then we're going to focus on the interval from 0 to pi over 2 because that's what we were told here. Now, cosecant is 1 over sine. So our sine function looks like this on the interval from 0 to 2 pi. But cosecant, well, it's 1 over sine. So it's going to be undefined every time that sine is 0. And the cosecant function kind of looks like this. It looks like these little U-shaped pieces. But on the interval from 0 to pi over 2, we're only interested in this piece. So I've got that piece and that piece. Secant is 1 over cosine. Cosine looks like this. And again, it's going to be undefined when cosine is 0. And that is pi over 2 right there. So secant looks like that. Again, has these U-shaped pieces. They're just off 90 degrees from these U-shaped pieces. We're only interested in the part from 0 to pi over 2. So the question is there any constant that you can multiply this by? And a constant that you can multiply this by, and a constant that you can multiply this by, so that when you add all of these pieces together, you're going to get 0. No. The only way that that could be 0 is if all the constants are 0. So we will say that C1, C2, and C3 must be 0. So that means the set of functions, and I'll just call them F1, F2, and F3, is a linearly independent set. Now in WebAssign, they actually gave us a little bit more information. I just said WebAssign, sorry, that's for calculus. This is MyLab Math. In MyLab Math, they give us a little bit more information. These are your options. So they weren't expecting you to use the Wronskian at all. On our quiz, I was expecting you to use the Wronskian. I'm going to be grading your paper, not grading the MyLab Math answers as much. But they say, choose from one of these. They say the functions are linearly dependent because this equation has solutions C1 equals blank, C2 equals blank, and C3 equals -1. So they're actually giving you C3. So they're saying if C3 equals -1, what would C1 and C2 have to be so that C1 times tangent of x plus C2 times cosecant of x equals, if I add this to the other side, secant of x. So again, look at these graphs. You might say, what do I multiply this by and this by so that when I add them together, I get this function? Well, there's no way I can add these two guys together and get that function. Like that's what we mean when we talk about linearly independent sets. We talk about one of the functions being redundant. In this case, this guy cannot be written as a combination of these two guys. There's no constant I can multiply this by except for 0, and then add to this to give me this. If I used 0 here, though, then I would have to multiply this by something, like just a constant to get that. And even though the shape is very similar, like there's no constant I can multiply this guy by to get this guy. And I say I have to multiply this one by 0 because this has like y values between 0 and 1, and this one doesn't have y values between 0 and 1. So in order for us to have no y values between 0 and 1, like we're gonna have to do something with the y values over here. So it's not happening. This is not possible. The only option is this. We say the functions are linearly independent because the equation has no solutions that are not all 0. So that is one way to solve this problem. I was expecting you to use the Wronskian, but any justified answer will do.